Better now? Yeah, okay. Okay, thanks a lot for the introduction, and thank you so much for the invitation. I'm very excited to share with you some insights on the study of quantum reference frames for spacetimes, and in particular, I want to talk about quantum reference frames for a particular regime that describes superpositions of spacetimes. And this is based on joint work with a number of great people, all of whom are actually attending the conference, so if you have any questions, do feel free to bother them as well. Now, in this talk, I want to talk in particular about 3 applications of quantum reference frames. So after a very brief introduction to one particular formalism to quantum reference frames, I want to talk about how we can use them as a tool for predictions at the interface between quantum theory and gravity, and then talking a little bit about how we can generalize these ideas to the context of superpositions of semi-classical spacetimes. I want to use them to formalize a quantum generalization of Einstein's famous Hall argument, so-called quantum Hall argument, and then talk a little bit about what this tells us about processes with indefinite causal order. So let's jump right in with a brief introduction to quantum reference frames. Now, we're all coming from rather different communities, so we might have different motivations for studying quantum reference frames. In Vienna, I think the most prominent one is a quite practical approach, where we say, well, in practice, anytime we describe a physical system with respect to a reference frame, like a clock or a ruler, this is a material system, and as such, it should ultimately be described, or at least describable, by quantum theory. So it makes sense to ask what happens if we take into account the quantum properties, like superposition or entanglement of the reference frame, leading to the notion of a quantum reference frame. But quantum reference frames also arise quite naturally in the study of quantum gravity, where already at the classical level of GR, the problem of time evokes a need for a reference frame in order to even describe evolution in time or change across space. And while this is certainly not the only approach, it is one way to then treat the systems that we use as reference frames in GR as quantum systems once we go to quantum gravity, again giving rise to a notion of a quantum reference frame. And finally, reference frames play an important role in gauge theory, although they're often not called explicitly reference frames, but they do allow us to construct gauge invariant observables through dressings. Now, depending on which field you're coming from, what your motivation is, you might also be familiar with a different formalism. And there have actually been many different approaches to quantum reference frames with slightly different mathematical formalisms and slightly differing realms of applications and motivations for studying them, ranging from trying to essentially describe the whole universe with a view from nowhere from which we can derive the different perspective, as in the perspective neutral one. Other people focus more on what we can measure relative to a quantum reference frame, as in the operational approach. People ask what happens if we lose access to a shared reference frame in a more quantum information context. And finally, if we're interested only to ever speak about the perspectives of different reference frames and how they relate, we end up what some people call the perspectival approach. Now, the precise relation between all of these approaches is still a study of ongoing research. But I want to stress that I'm only going to be talking about ideal quantum reference frames, and for these, the perspectival and the perspective neutral approach are actually shown to be equivalent. Now, quantum reference frames are also closely related to a plethora of other fields in this community, such as edge modes, material reference frames in quantum gravity, type reduction, which I think we're going to be hearing about in the next talk, superselection sectors in quantum information theory, and symmetry principles. And it would be absolutely impossible to touch upon all of these in a 30-minute talk, so I'm going to be focusing on like a very small part of this. So the approach I'm going to be working with is the so-called perspectival approach or perspective-dependent approach that dates back to the work of Giacomini, Castorese, and Bruckner. And in particular, I want to focus on how we can use these quantum reference frame transformations to formalize extended symmetry principle and use them to better understand the interface between quantum theory and gravity. Now, reference frames and symmetries are really closely connected. And I think the most simple example we have for this is a translationally invariant theory. If you have a bunch of point particles floating in outer space, there's no absolute meaning to where they are positioned within absolute space. And the laws of physics won't tell any difference if we move the whole system relative to this absolute space-time background. And this corresponds to a free choice of position reference frame, whereby position reference frame here, I really just mean we can put the 0 point of our coordinate system anywhere we want. We can attach it to the blue particle or to the orange particle, and we can easily transform between the two simply by shifting everything by the distance between the old and the new reference frame. Now, what if we consider not classical particles, but quantum particles? And in particular, particles that could, for example, be in a superposition with respect to one another. well then a simple classical translation is not going to allow me to go into the reference frame of the orange particle, which is now in a superposition of distances to the old reference frame. Instead, what we have to do is a superposition of translations. That is, we do a different translation depending on the distance between the old and the new reference frame. And we can do so with a quantum-controlled translation operator, which you can see here. So essentially, this is just the standard translation operator of quantum theory, except that now the amount by which I translate, okay, it's not working. The amount by which I translate has turned into a quantum operator. And now if we apply this to the quantum state, which is just a product state on the left-hand side, we go to the new state of the reference frame, we find two interesting features. We find that now the orange particle, the new reference frame, is definite, while the other particles appear to be in a superposition. And what is more, the state of the quantum system actually tells us that they are entangled with one another. So we already learned from this very simple example an important feature of quantum reference frame transformations, which is that superposition and entanglement are actually frame dependent. And we're going to make use of this throughout the remainder of the talk. Now, as I said, classically, we know we have an invariance under classical translation. We can jump into the reference frame of any particle. And a priori, I think it's quite reasonable to assume that this is also true if we jump into the reference frame of a quantum particle. And we can make this more formal by formulating a so-called extended symmetry principle, which actually just has two ingredients. We have the symmetries of our known physical theories, like translation invariance, and we combine it with the linearity of quantum theory that allows us to consider superpositions. And with this, we have an invariance not under classical symmetry transformations, but under quantum-controlled symmetry transformations, so-called extended symmetry principle. Now, I've been only talking about the translation group, but let me stress that this has been generalized to many more groups, just the Galilei group, locally compact groups, spin rotations, conformal transformations, Lorentz boosts, and quantum diffeomorphisms, which I'm going to be talking more about in the second part of this talk. But I want to start by sticking with the translation group, because there's already a lot of interesting insight we can gain with the simple example of just a three-particle system and a quantum translation. And in particular, just as we can use changes of coordinates to simplify our physical problems, we can use changes of quantum reference frames to simplify problems that we might not be able to solve otherwise. And one particular example of such a question that we cannot solve with known physics is the following. Imagine we have like a massive object. I'm depicting here the Earth. More realistically, we're probably going to put like little gold spheres in superposition. But imagine we can place a massive object in superposition, and we want to determine the motion of a test particle in the gravitational field of this quantum source. Well, quantum theory and general relativity on their own will not give us an answer to this question, because they don't tell us what is the gravitational field sourced by a quantum object. We could, of course, make assumptions about the quantum nature of the gravitational field, but what if we don't do that? Well, then there's another strategy, which is to change into the quantum reference frame in which the gravitational source becomes definite, just as we jumped into the orange particle beforehand, and now the test particle will appear in a superposition. But this is a much nicer situation, and in fact one that we have tested experimentally. We know how a quantum probe in a superposition falls in the gravitational field of the Earth. So we can use known physics, geodesic motion, plus compute the quantum phase that is picked up by the particle to determine the path of the particle. Now we fall in a superposition of geodesics. And then we can invoke our extended symmetry principle and transform back using the inverse quantum reference frame transformation, importantly assuming that the change of quantum reference frame is a symmetry of the equations of motion. So here we're invoking the extended symmetry principle. And we find that, again, the test particle falls in a superposition of trajectories and, in fact, gets entangled with the massive object in superposition. Now, I'm not saying this is what it must be like. We still need to experimentally test the extended symmetry principle. But if you believe that it's reasonable to assume that the laws of physics are not invariant under just classical changes of reference frame, but also under quantum changes of reference frame, you might want to question some of the other theories that are around for predictions in this realm. So we have seen that using the extended symmetry principle, we can import the result that we know to be true, that a test particle in a classical gravitational field will fall in a superposition of trajectories, and we infer through the extended symmetry principle that it also must fall in a superposition of trajectories in the original reference frame. Now, any other theory will have to agree on the frame of the mass. Otherwise, they would have already been ruled out. But if we look at collapse models, for example, they disagree with the extended symmetry principle, because they would say, well, the state will necessarily collapse in a very short amount of time, and the particle will fall either to the left or to the right with a certain probability, thus violating the extended symmetry principle. Similarly, for semi-classical gravity, if we put the particle right in the middle of the two locations of the massive object, the gravitational field would average to be 0 at this point, and the particle will not move at all. And again, we find that both collapse models and semi-classical gravity are kind of implicitly assuming a preferred quantum frame of reference. Now, if we do believe in the extended symmetry principle, there are still a lot of theories that are compatible with that. I think in the low energy regime, linearized quantum gravity, which is generally widely accepted in any case, agrees with this. And more generally, it's consistent with just assuming that the gravitational source in superposition also sources a gravitational field in superposition. And this is what we're going to be assuming throughout the remainder of the talk, where we're going to speak about spacetimes in superposition. So let's say we do actually manage at some point to place a massive object in superposition, and it sources this gravitational field in superposition. How can we describe the situation? Now, I should stress that when I say superposition of spacetime, I mean something very specific, which is a superposition of states of the gravitational field peaked around some semi-classical configuration of the metric, like a coherent state for the gravitational field. And this is something we would expect in a particular regime of a potential theory of quantum gravity. Let me stress again, this is not making too many assumptions. Like if we have some theory of quantum gravity, we definitely want to recover GR, so we need to have some kind of semi-classical limit. And if we assume that the linearity of quantum theory doesn't break down in this limit, it also makes sense to consider superpositions of these semi-classical states. However, of course, it's only a very small regime of a potential full theory of quantum gravity. So it is complementary to the full approaches, which often look at the high energy regime, where we would expect completely different effects. But it is an interesting playground to investigate conceptual questions. And in particular, there's one conceptual question that we briefly touched upon yesterday as well, and that is, what does it even mean to say that the Earth is in a superposition of locations in such a scenario? Now, if we have some fixed space-time background, this is a very trivial question, right? It's in different locations with respect to that space-time background in each branch of the superposition. But if we no longer have a fixed space-time background, we have a superposition of arbitrary spacetimes, then there is no a priori matter of the fact whether the Earth is in the same or different locations across the superposition. We could try to pick some coordinate fields and say, well, in one branch it's a coordinate position 2, 1, in the other one it's a position 2, 3. But then we have the diff invariance of GR, which tells us that we can just arbitrarily reshuffle the coordinates, and there is nothing that would prevent us from reshuffling them differently in each branch of the superposition, so that with respect to the new coordinates, the Earth now appears to be in the same location, appears to be definite. And what I want to ask now is, how can we find a way to identify points across the superposition of spacetimes? And the answer is that we can do that by choosing a quantum reference frame. And we kind of did this implicitly in the case of the translation group already, where in the frame of the massive object would be definite, would be in the same location. So we're kind of identifying the points at which the massive object resides. And similarly, we could go into the reference frame of the test particle and identify its location so that it would appear to be definite or in a superposition. Now, importantly, if we are dealing with spacetimes in superposition, a single point particle will not be enough to get rid of the redundancy of the diff invariance. So instead, we have to extend our quantum reference frame. And in particular, what we can do is, instead of looking at single point particles, we look at sets of scalar fields. We pick 4 scalar fields, which I denote here by chi A. And now I say I identify a point P in one of the manifolds, M1, with a point Q in the other manifold, M2, if the values of these scalar fields are the same at these 2 points. And I can formalize this by simply taking the point, looking at the value of the scalar fields chi, C1, C2, and so on, and then finding the point Q at which the values of the fields are the same. So I use the coincidences of these scalar fields chi to identify the points across the spacetimes in superposition. And if I compose these 2 maps, this gives me a map between the 2 branches of the superposition, which we call here the comparison map, and which is very closely related to the counterpart relation that we heard about yesterday. Now, I should make an important mathematical caveat. In general, of course, this will not be a bijective map. in order for this to be a bijective map, the fields need to be either inhomogeneous enough so that we can really uniquely associate each point P in M1 with one unique point Q in M2, or if that is not possible, we have to do the same as we do when we pick a coordinate system, which is restrict to some open subregion of the spacetime, and just use the set of scalar fields within that subregion. Now, I should also comment briefly on what we mean by these scalar fields. So far, they've been really abstract. And there's different approaches to modeling reference frames, already in classical general relativity, but also in quantum superpositions of spacetimes. And essentially, we can distinguish three options that depend on how much does the reference field interact with the spacetime. There are the completely idealized or coordinate fields, which don't feel the spacetime at all and also don't backreact. But we could also consider dynamical fields, which do feel the spacetime background, like Klein-Gordon fields in a curved spacetime, but they're not heavy enough to contribute to the gravitational field itself. And finally, you could consider fully dynamical fields, like dust fields, or even fields constructed out of the metric tensor itself that both feel the metric and influence the metric tensor. Now, if you have a preference for one of these three, feel free to just stick with whatever you prefer, because what I'm going to say is going to work for any of these. But depending on the concrete application, you might prefer one or the other. The idealized coordinate fields, they give you more freedom. You can choose absolutely any configuration, whereas the dynamical reference fields are more realistic and take into account more physical properties of the reference frames. Now, I said before that the choice of how we identify points across the superposition is related to a quantum reference frame transformation. And we can now make this more precise by identifying with the choice of a quantum reference frame a choice of these scalar fields. So usually we have more than one set of scalar fields in our spacetime. We might have Klein-Gordon fields and dust fields and also the metric fields. And depending on which one we choose, this corresponds to a different choice of quantum reference frame. And the transformation between two such choices of quantum reference frame now importantly consists of two steps. There's the quantum-controlled symmetry transformation that we already saw in the case of the translation group. But importantly, the second step that was implicit in this previous example is that we also need to change the way we identify the points across the superposition. We need to change the comparison map from identifying the points with the same values of the chi fields to the points with the same values of the chi tilde fields. And now I should stress, I don't have the time to go into this, but this is actually all super closely related to what Enrique was talking about yesterday. We can see a choice of quantum reference frame as a choice of sections through the space of models, which then comes with a preferred counterpart relation, which in this case is just a comparison map. But I don't want to lose too much time on the formalism and speak more about applications. And now that we understand how to identify points across the superposition and how to apply quantum reference frame transformations to arbitrary superpositions of spacetimes, we can actually gain some new insight on a very old problem, which is the Hall argument. Now, I'm sure many of you are familiar with the classical Hall argument, but I want to very briefly repeat it here. And essentially, the classical Hall argument can be seen as an argument against spacetime substantivalism, the idea that spacetime points themselves have some physical or metaphysical meaning. And this is an argument that Einstein made when he was concerned about general covariance. And the idea is the following. You take your spacetime, you cut out like a small region, the hole, and now you perform a diffeomorphism that only changes how the fields inside the hole are distributed across the spacetime manifold. And the diffeomorphism becomes the identity at the boundary. Now, because of the diff invariance of DR, you now seem to run into a problem, because you can know everything that is going on around the hole and not be able to predict what is happening inside the hole, because Einstein's field equations are compatible with both this and this configuration. So we seem to have an underdetermination. There is, however, a simple way out, which is to simply claim that these two situations, are not different physical situations. They're actually the same physical situation, but with a mathematical redundancy. And if we do this, this also means the way that the fields are distributed over the spacetime points, which is the thing that the diffeomorphism changes, has no physical meaning. So spacetime points themselves should not be attributed too much metaphysical meaning. Now, I think this has been widely accepted for most people working in GR and quantum gravity, and one can actually deal with this relatively straightforwardly by getting rid of the redundancy by simply using point coincidences of physical fields instead of speaking about the metric tensor at an abstract spacetime point. We can just speak about the metric tensor at the point where two world lines cross or at the point where my dust fields take certain values. And in classical GR, this is enough to get rid of the problem. However, the situation is a little bit different if we consider superpositions of spacetimes. Because now we have an additional property that we can look at, which is the localization of events. So when I say a pair of points, P and Q, across the spacetime manifolds in superposition is localized with respect to a given choice of quantum reference frame, I just mean that they're identified with this comparison map that we saw earlier. And we can now ask ourselves what happens if we apply a quantum reference frame transformation. As I said before, the first step of a quantum reference frame transformation is this quantum-controlled diffeomorphism. So we apply a general different diffeomorphism in each branch of the superposition, and the diffeomorphism, treating it actively, acts on both the points, because I want to see them as like physical events and not just abstract manifold points, and on the scalar fields. And we can now look at what happens to the identification between the points. Now, this is a bit of a complicated calculation, but not too bad. We simply see that if we apply the diffeomorphism both to the points and the scalar fields, which define the comparison map, everything cancels out nicely, so that actually the pair of points d1 of P and d2 of Q remains localized. So a quantum diffeomorphism alone does not change the localization of events. But, as I said before, this is not the only part of a quantum reference frame transformation. Importantly, it also changes what we mean by the same or different points, because now we identify points using a different set of scalar fields. And because the map C chi is constructed from a different set of scalar fields than C chi tilde, and we already saw that using the old reference fields keeps the localization intact, we can now infer that the localization will no longer hold in the new choice of quantum reference frame. So the pair of points d1 of P and d2 of Q will be delocalized in the new frame of reference. We find that the localization of events is a reference frame dependent feature, just like superposition and entanglement are reference frame dependent features when taking into account the quantum properties. And this actually allows us to formalize a generalization of the classical Hall argument. Because we've already kind of taken into account everything that we learned from the classical Hall argument. We didn't speak about abstract manifold points. We used physical scalar fields to identify the points across the superposition. And yet again, we found an ambiguity, namely in the choice of which reference field we use to identify the points across the superposition to define these coincidences. Which leads us to the slogan of the quantum Hall argument, identification is pointless. Now, this has been all very abstract, but I do want to convince you that this actually has practical applications, and that understanding these identifications across the branches is actually relevant for conceptual questions at the interface between quantum theory and gravity. And one particular example is the study of indefinite causal order. And we're going to hear a lot more about indefinite causal order in the afternoon session. So for now, let me just say that when I say I have a process with indefinite causal order between two events A and B, this just means that I cannot describe it in terms of A before B before A, or a classical mixture thereof. Now, a particular prominent example of a process with indefinite causal order is a so-called quantum switch, where I have some target system, and depending on the state of a control system C, I apply either operation UA before UB or UB before UA, leading to an indefinite order of these two operations. Now, there are different implementations of this abstract process, one of which has been realized experimentally, the optical quantum switch, and one of which still has the status of a pure Gedanken experiment, the gravitational quantum switch. Now, in the optical quantum switch, the target system could be an electron or a photon that I send along a superposition of paths, so the path becomes the control system, and depending on the path, I either pass through Alice's laboratory first and then through Bob's laboratory, or the other way around, so the order of their operation is going to be in a superposition. Now, this has been realized in the lab. However, maybe you're a bit unhappy with this because the superposition of causal orders does not come from space-time causality. So people have devised a Gedanken experiment where the indefinite causal order is actually induced by a superposition of space-time backgrounds. So we can again imagine we place a massive object in a superposition, and now instead of performing the operation when the particle hits the laboratory, Alice and Bob have their wristwatch and perform the experiment, perform the operation at a particular proper time tau. But because the space-time background is in a superposition, whether Alice's proper time tau is before Bob's or the other way around, depends on the branch we are in, again leading to a superposition of indefinite causal orders. And there is this ongoing debate now between people who believe that the quantum switch has been experimentally realized because they say, well, the optical switch is a good enough implementation, and other people who say, well, in order to really realize the quantum switch, we need to do the gravitational experiment. The optical one is just a simulation. And at the core of the debate is really the question, what do we mean by an event? Do we mean the space-time point at which we apply the operation? This is the story that what one could call the spatiotemporalists tell themselves. Or do we mean the application of the unitary? And depending on which camp you're in, you would say in the optical quantum switch, because they applied at different times, you either have indefinite causal order between two events, or you have definite causal order between two pairs of distinct events, the four different space-time points. Now, I do believe that studying this in a different quantum reference frame can actually give us some interesting insight on these two perspectives. Because we already saw that the change of quantum reference frame can change whether two events are localized. So whether we associate to them different space-time points or the same space-time points. So in a way, the change of quantum reference frame can change the number of events in our description of the optical or gravitational quantum switch. And we can see this quite explicitly by simply modeling the application of the unitary by considering like an intersection of world lines where the target system hits Alice's or Bob's laboratory. And let's say we start in a description that is similar to the one in the experiment. We have a flat space-time background across both branches, but the paths of the particle are delocalized. And the particle crosses Alice's and Bob's laboratory at different space-time points, according to this identification. However, we can always find a quantum reference frame change such that the two events are associated to the same space-time point across the two superposition. Now, as a side effect of the quantum diffeomorphism that we have to apply, now we would find the metrics appear to be in a superposition. So we've gone from a situation with delocalized events on a fixed space-time, as in the optical quantum switch, to a situation with localized events in a superposition of spacetimes, as in the gravitational quantum switch. Similarly, we could go the other way around. We could start with localized events on a superposition of spacetimes, and while we cannot make the spacetimes entirely definite, we can at least make them definite along the path of the target system, which is the part relevant for the experiment. And then we can just go into Fermi normal coordinates along the path of the particle, so that again we have delocalized events, but now we have a flat metric along the path of the target system in both branches of the superposition. And we can actually formalize these insights in a no-go theorem, which essentially states that there is no quantum coordinate system in which the following three statements hold. One, we have indefinite causal order between the events EA and EB. Both events are localized, and the space-time metric is definite. But importantly, which of two or three is the underlying reason for the indefinite causal order depends on the choice of quantum reference frame. Whether indefinite causal order is due to delocalized events or a superposition of spacetime metrics can change under a change of quantum reference frame. So really what this tells us that we should maybe not take the spacetime localization and spacetime location of the event as a relevant property in assessing the question of whether we have realized indefinite causal order. And as I said, whether it is due to a superposition of spacetimes or delocalized events will depend on the choice of quantum reference frame. Now, I hope that this convinces you that there's at least one helpful application of thinking about quantum reference frames in a superposition of spacetimes. I do believe that there's a lot more to be uncovered. But for now, let me summarize some of the main results. We saw that the invariance under quantum reference frames allows us to formulate extended symmetry principles. Invariance under quantum controlled transformations can be used to make new predictions for the scenarios at the interface between quantum theory and gravity. We saw that in the context of superpositions of spacetimes, the choice of quantum reference frame corresponds to a particular identification of points across the superposition. This allows us to formulate a quantum generalization of the Hull argument, which tells us that we shouldn't assign too much physical meaning to this identification and the spacetime localization of events, which in turn tells us that whether indefinite causal order is due to delocalized events or superposition of spacetimes depends on the choice of quantum reference frame. Now, I want to close this talk by a little outlook. I think what the study of reference frames already at the classical level, but now more recently quantum reference frames, has shown us that there are a lot of properties like superposition, entanglement, subsystem structure, localization of events, and even what it means to be the same or different across different branches of the superposition depends on the choice of reference frame and is thus relational. And we can ask ourselves, what other properties that we previously thought to be absolute might turn out to be relational when we talk about quantum superpositions of spacetimes or quantum gravity more generally? With this, I would like to thank you for your attention.